In the last few examples, we've been proving statements of the form if P, then Q. Written equivalently, we've been proving that P implies Q. Here's another example. Let's let P be the statement that n squared is odd. And let's let Q be the statement that n is odd. And we'd like to prove, we want to prove that P implies Q. Okay, simple enough. What's our first step? Our first step is to assume that P is true. So we'll assume n squared is odd. Okay, now we need to conclude somehow that n is odd. So our next step is probably, since n squared is odd, and we have a formal definition of what it means to be odd, say that n squared can be written as 2k plus 1 for some integer k. Now we need to show that n is odd. Well, it becomes sort of difficult to conclude at this point. I know that n squared equals 2k plus 1, so I guess I know that n equals the square root of 2k plus 1. But how do I know that this square root of 2k plus 1 is odd? I need to show that the square root of 2k plus 1 can be written in the form 2 times some integer plus 1. At least it's not clear to me how to proceed here, so we might want to try a different proof strategy. It turns out that whenever you want to prove a statement of the form P implies Q, it's equivalent to prove that not Q implies not P. This is often referred to as a proof by contradiction. And not Q implies not P is often referred to as the contrapositive of P implies Q. I would suggest that you sit down and think, offline, why is it that proving P implies Q is equivalent to proving not Q implies not P? And in any event, I would memorize the fact that proving P implies Q is equivalent to proving not Q implies not P. So this gives us a new strategy for proving that P implies Q. Our first step could be, well, let's first instead decide to prove not Q implies not P. Because as we just said above, that's equivalent to proving P implies Q. Okay, well, if we want to prove that not Q implies not P, we should assume that not Q is true. What is not Q? Not Q is n is even. Okay, so we'll assume this is true. This is not Q. And what do we want to conclude? Well, we want to conclude not P. So we want to conclude that n squared is even. Okay, so since we know n is even, n can be written as the form 2k, where k is an integer. Okay. Remember, we want to conclude that n squared is even, so let's square n. This is the same as squaring 2k. And so we see that n squared equals 2k times 2k. Could write this out even further and say that n squared equals 2 times k times 2k. Okay, so we've written n squared as 2 times some integer. Again, we've written n squared as 2 times some integer. This implies that n squared is even, And the statement n squared is even is exactly not p. Again, we started from not q, namely n is even, and we concluded not p, namely n squared is even. So we've proved that not q implies not p, and that's equivalent to proving p implies q, which is what we originally wanted to prove. This is a classic example of a proof by contradiction. Here's another simple proof by contradiction. Let's say we want to prove that if n equals a times b, where a and b are positive integers, then either a is less than or equal to square root of n, or b is less than or equal to square root of n. Okay, so here we have mathematical statement, call it p, and here we have mathematical statement q, and we want to prove that p implies q. Instead, we're going to prove that not q implies not p. And remember, we said that it's equivalent. Proving p implies q is the same thing as proving not q implies not p, or proving not q implies not p is equivalent to proving p implies q. They're equivalent. So what is not q? Well, not q, how do we negate q? Q says either a is less than or equal to square root of n, or b is less than or equal to square root of n. So not q, by De Morgan's law, is a is greater than square root of n, and b is greater than square root of n. Okay, so now we want to show that not q implies not p. So step one is to assume that not q is true. So a is greater than square root of n, and b is greater than square root of n. Let's multiply a times b together. Well, a and b are both positive integers, so their product, since a is strictly greater than square root of n, and b is strictly greater than square root of n, a times b is going to be strictly bigger than n. Okay, but now we've contradicted p, right? P says that n equals a times b. But if n equals a times b, there's no way that a times b could be strictly greater than n. It's a contradiction. So we can conclude that not p is true. Once again, we started from not q, we arrived at a sequence of simple steps to not p, and so we can conclude that not q implies not p. Therefore, equivalently, p implies q. So we know that if n equals a times b, then either a is less than or equal to square root of n, or b is less than or equal to square root of n. Again, this is a proof by contradiction because we started by contradicting q, and we ended up contradicting p.